Okay, in this section we're going to cover the 3, 4, 3, 5 notes on adding and subtracting fractions. So as one would expect, they start out with the simplest, adding fractions with like denominators. So that is, here are some examples of an activity sheet that you can use, and you can either have it as a solve for the red, which is going to be the sum, or determine the missing add-in. So either way, this is a nice little practice example. Okay, I do find that explaining addition of fractions with fraction strips is very helpful in preventing students from just going crazy and adding the denominators together, adding the numerators together, all in one fell swoop. They kind of go on autopilot, and that's the result of addition. But when you tie it into this fraction strip, I think it's very helpful. I also think it's really helpful, to use words for your denominators, because that makes it appear different than your regular addition. So here you would be less inclined to add that as a 15th to this. You would be instead inclined to add the 4, the 7, and get 11. And once you've developed those good habits, then when you convert to not having your number line and your fraction strip, you may continue to do those good habits and not touch your denominator. So I thought this slide was a nice way to bridge between adding same denominators and the logic behind what you have to do to add when you have different denominators. So once again, the authors are using words for your denominators here and here, and numbers for your numerators. And visually you can see that you couldn't really add, for example, 1/12 to 1/4. Okay, so since you can't do that, we have to have some kind of strategy to be able to do it. So you have, the visual strategy, but then here you're tying in the visual with an actual practical approach as an algebra problem, and in it you're pulling in the identity property of multiplication. Okay, so as long as you do this, as long as you multiply by 1, you can always do that. Algebra police will not get you, and you'll be able to convert your 5/6 plus 3/4 into a problem that you can actually add by changing the numbers to 20 over 24 plus 18 over 24. I think the authors did a good job of explaining how to get a common denominator, and clearly the simplest is always just to multiply your denominators together. That will always be the common denominator. And proceed from there, and then reduce at the end. Or, depending on where your kids are in the learning process, you could have them list out all the common denominators and then figure out the least common, so that they don't have to then reduce or simplify their fraction at the end. Either way, you'll get to the same answer. It just depends on where your particular students are in this process. Okay, I put this little link in to Math is Fun. It even has a little song about adding fractions with unlike denominators. So I thought, if you find that beneficial, great, use it. So next they go into writing mixed numbers as improper fractions. So you clearly want to point out, you have the whole number component, and then you have the fractional component. And depending on where your students are in the learning process, you may be using fraction strips to explain this, or other kind of manipulatives to do so. So we're going to talk on the next slide about converting from mixed numbers to improper fractions and back again. So first off, when you compare a mixed number or a mixed fraction to an improper fraction, the difference is one has a whole number present and the other has a situation where your numerator is greater than the denominator. Okay, so here are some practical steps to convert a mixed fraction to an improper fraction. So you can multiply the whole number by the fraction's denominator, add that to the numerator, and then write the result on top of the denominator. So here is a step-by-step procedure. Here is a more colorful step-by-step procedure. And then here's a more visual. You can use fraction strips as well. Or another thing you could do that our authors did not mention is you can convert your mixed number into an addition problem, because this is really 1 and 7/12. So n means addition, so it's 1 plus 7/12. Okay, 12 over 12 is an equivalent fraction to 1 over 1. Now you have the same denominators, so you proceed as you would in addition of fractions. And you can even, if you wanted to, write it as 12 twelfths with the twelfths written out, plus 7 twelfths, again the twelfths written out. Add the 7 and the 12, get 19 twelfths, again the 12th written out. So here is, let's move on to the next slide at this point. I found this slide on the internet, and I thought this was a nice way to connect your mixed number, and as you're converting it, so what's the rationale for saying 3 times 12? You can tie it into a fractional representation of the whole number. So you have 3 times 4, that gives you 12. Why is that the case? Because you really have 12 thirds. Next, you're going to add the 2 you already have as a partial whole number. That gives you 14. So now you have 14 thirds. So you've added, and what's nice is they put numbers inside each third. So I thought that was also very clever and very visual. And you end up getting 14, because the last number I'm seeing right here is 14. The segments were all in thirds, and what's nice too about this slide is that they really stress keeping your denominator the same as it was when you began the problem. So I really liked that whole visual of going through it. And it would be nice to even have, especially some of you maybe older kids, create this visual for themselves to explain the steps that they're going through. And these could be, posters all around the classroom. So another approach, converting improper fractions to mixed numbers, is to set up a division problem. So again, this is going to be for the higher level students. You're not going to be doing this necessarily with your freshmen, with your kindergartners. So, another approach, and you can certainly bridge to this once they understand this concept. So I snipped activity 3P from our textbook into this slide because I thought they had some good approaches here. So this opens the door to analyzing errors. So clearly this wouldn't be day 1 of your fraction, addition, and subtraction exercise. But later on, as students start to be making errors, you could even save some of those errors and don't put names on them clearly, but see if students can recognize what's wrong, why it's wrong, and how to correct it. So for example, in the student 1 problem, what's happening is the student recognizes that they cannot take 3/4 from 1/4. So that's all good. The problem is when they borrowed from the whole number 3, they borrowed in tens because they had perhaps some base 10 confusion. So you clearly are borrowing 4/4, so that's going to make that 5/4. So that's a good thing to clarify. And here this student's doing it correctly. So now they, with the exception of one thing, they forgot that when they borrowed the 4/4, it makes this fraction now 5/4 because they already had 1/4 there. So you have the borrowing concept down a little bit, but they're still making some errors. Then as we move down to problem B, so it says there are 2 1/3 cups of milk in a bowl. How much milk must be added to the bowl so that there will be 3 cups of milk in the bowl? So you could do this problem as an add-on problem, like the cashier example, where they add on, and you speak in terms of thirds at this point. So if you have 2 1/3, they're counting on as well. So now they want 2 2/3, and they want 3 then. So they added 2 more, but what did they add? They forgot their units, so they added 2 more thirds. So they really have to add 2/3 cup of milk. Okay, so then there were 5 pounds of apples in a bag. After some of the apples were removed, so you have an unknown amount being removed. From the bag, there are 3 1/4 pounds of apples left. How many pounds of apples were removed? So this child is trying, had 5, realizes something's happening with 4, but so they have fourths. So here's a whole fourth. So if you take 4/4 out, that brings you down to 4 pounds. But you're not quite there yet because you have to get to 3 1/4 pounds. So they're trying to break up the last fourth, but really what they want to do is realize that I have a whole nother, whole unit to deal with. So that procedure is not going to get them there. So I was thinking about what are the things you can do with this if you had this kind of problem. Could you rewrite 5 pounds in terms of how many fourths of pounds that would be? And so you end up multiplying 5 times a fancy 1, 4 over 4, and then you have 20 fourths, and now you're subtracting another mixed number. Well, why don't we make that an improper fraction as well? So that's going to be 13 fourths, and that may be a better way to get to your answer, which is 7 fourths, but since they want to know it in pounds, I would say that that was 1 3/4 pounds. So that will get you there. So you see that they have the 1, but it's the remaining 3/4 that they're not handling correctly. Okay, so looking at part D, I thought this is an interesting problem as well. So the child's adding 2 2/3 plus 1 2/3. So they correctly add the whole numbers and they get 3, but then what they're doing is they are counting 4 out of 6 pieces, but that's not what we want them to do at that point. So you have 2/3 plus another 2/3, and if you write out thirds as a word, then perhaps they would say, I have 4/3, and then recognize that that is 1 1/3. So you're going to add 1 1/3 to the 3 wholes you already have to get 4 and the 1/3. So again, it was what part of the whole you're talking about. Your whole is thirds, your whole is not sixths. So I really think that's a very good discussion problem. Okay, this last problem I think is also good because you can handle it at many different levels. Find at least 2 different ways to calculate. So I think by even saying that, you're stressing that there is more than one way to solve a problem, which is an important thing for all students to understand, because that is certainly true as they get older, and sometimes they only want to do it one way. The fact that this problem is asking a child to think of more than one way is going to help them grow in this mathematical experience, and it'll help them in other subjects as well. There's more than one way to understand, a story. There's more than one way to do a science experiment. There's more than one way, to get home from various places in their lives. So clearly, depending on where they are and what you want to stress, there's going to be different ways to handle this problem. So I think this exercise of working with decimals was very valuable. So for on many fronts. For one, most people hesitate a little bit in naming decimals. So the convention that you name it by the highest place that you observe, so that's going to be 752 thousandths for that reason. But when you expand it in this fashion, you get the sense of why you do want to call it thousandths, because that's acknowledging the common denominator. So it's kind of an eloquent way to do it, and it serves, as I said, many purposes. So I just realized I put one slide in front of the other, so let's go back to this. So the concept that you have finite decimals. So decimals that come to an end. That finite is an interesting concept, I think, for kids who may not appreciate the infinite nature of some decimals, such as pi or e. So having them convert from decimals to fractions is awesome, because a lot of times as they get older, they want to keep everything as fractions, and they don't even really view a number like, say if you had, instead of 4.6, you had 4.666, which might be written as 4.6 with bar notation. They view this as the same as that, and that is absolutely not the case. So you cannot write an infinite decimal as a fraction. And so therefore, your 4.6 will always be less than 4.6 bar notation, and you can't just write it as a fraction. Okay, so that's good things to think about as you're teaching it at your elementary level. At the high school and college level, other issues come up. So once again, you're reinforcing the fact that a decimal, a finite decimal, can be expressed as a fraction. And then your second step here, we're getting a common denominator, which is going to allow us to write our fraction as an improper fraction. And when you see this, you recognize, oh, wait a second, I can call this 4 6/10, but I can also call it 46/10, which is a nice concept for them to understand, that there may be more than one way to say a number or say a decimal. So I know this little section was a very small section, and the authors talk about when combining is not adding, and they give the example of the bananas and the blocks. So I wanted to explore this a little bit more, because this falls nicely into the whole algebra world. So let me extrapolate on that on the next slide. Okay, so now that I have this whole slide put together, we can talk about this some more. So the authors make a good point of saying you can't add, apples and oranges, or in this case, bananas and blocks. So that is true on many levels. So algebraically, which is what the kids will be doing when they get to high school, we run into problems when we have what we consider bananas and blocks or apples and oranges, and the kids don't view it that way. So when you add your 3 bananas and your 4 blocks, you can say that you have 7 items, but you can't say you have 7 banana blocks. Okay, you can't make them into the same item. So similarly, for algebra, if you viewed bananas as x's, you would have 3 x's, and then you're adding, if you view the blocks as y's, you could not say that you have 7 xy's. So for that same subtle reason of what you're doing back in elementary school, it carries through in high school. Okay, another problem we have is when the terms are almost alike. So instead of saying, let me just undo that. Instead of saying that we had 4y, what if we had, I'm going to do that again. What if we had 4x squared? Okay, so some of my kids will think, well, close enough. I can call that, 7 whatever, x squared, 7x. I can combine them, but they cannot. So the grade school reasoning holds through high school. I also thought it was a nice discussion about the unlike wholes. When you're combining, a third of a pie with a fourth of another pie, the underlying concept is that the pies are the same size. And so if you give them the same word, they mean the same thing. So when that's not the case, you have to be explicit about it. Because these may both be pies, but because they're different sizes, the wholes are not the same, and therefore these are really not items that we can add together and combine in any kind of fashion. Okay, so I thought those were some subtle things that are actually very valuable for high school students to have had reinforced when they were in grade school. So the textbook next goes into 3.5, which is adding and subtracting with negative numbers. So our textbook does a nice job of using temperature to show the addition of a negative or positive, and then it generalizes it to variable terms, and really it's identifying additive inverses. So additional insight can also be provided by using a number line, and if you were going to add a 2 and a negative 2, that brings you back to the center, to the origin, to the 0. Okay, another thing that's interesting about this is it kind of ties into absolute value. So absolute value is this symbol. So the absolute value of negative 3 is 3, because absolute value is telling you the distance from 0. So the absolute value concept feeds nicely into the additive inverse concept. So just things to be aware of as you're teaching. You are building the foundation for further thinking when they become high school students and beyond. Okay, my pet peeve is when my students, and very few of them do this, but they leave an answer or they leave an expression as A plus parentheses negative B. And a lot of times they don't even use the parentheses. So they would have A plus a negative B as their final expression. And that's a big no-no. You only want to have one operation in a number sentence. But using it as a stepping stone is completely appropriate. So the connection by adding a negative, that connection that is the same or equivalent to subtracting away a positive is a very important concept. So the more you can work to get that across, the better. And I think, jumping on the number line is very, very helpful in the idea of what's positive movement and what is negative movement. So we'll discuss more of that in the next slide. Okay, so in this last slide, they talk about the direction of the movement. And again, depending on how old your students are, you may, take this further and further and bridge away from a number line. But the number line, no matter how old they are, it's nice to take it back to the fundamentals, because sometimes when they were first exposed to the fundamentals, their brain was not ready to take it in. So going back to the fundamentals is sometimes exactly what's needed. So when you're on a number line, clearly if you're at 2, if you're at 2 and you're going to add, you're moving to the right, and you're moving to the right 5 places, and so you'll get to 7. Now, another thing about a number line, it's a nice bridge to start talking about not always counting up by 1. Like, what if you were going to count by 2s? How would that look? Well, you can still start with 0, but you're going to be having these increments instead. Because many times when I have my students graph things, they are so fixated on they have to go up by 1. Well, sometimes that's highly inappropriate, and you'd be adding reams of paper to your graph in order to really go up by 1s. So as they get older, having different gradations and stressing the fact that if you have different intervals, they have to all be the same. You can't throw a 3 in there because that happened to be in your data. Okay, so all of that is a good thing that you can bridge with while doing simple concepts like addition. And some of the kids won't grasp it because they're not quite there, and that's totally fine. But even if you have a couple that are kind of starting to think along those lines, you have, satisfied their need, their curiosity, and you have them thinking about how they can expand on what you're currently doing to something, down the road in the future. So subtraction, again, there are these cute little graphics. Subtraction is going to be moving to the left. So if you're at 7 and you subtract away 3, you're moving to the left. That's also the case if you're at 7 and you add a negative 3. You are going to be moving to the left. So all of this stuff is very foundational and extremely important.